All right, so we got the recorder on. All right. So where should we start? Well, let's start with instructions that you have seen already. So what we'll do today is to look at instructions from several perspectives. The first perspective is to go to the opcode table and look at the documentation of, okay, what does a particular opcode does? And we'll start with something that we have seen already. Let me change the zoom ratio here. And we'll start with LD, okay, which is an instruction that we have talked about several times. So are there any questions about the LD instruction, the load instruction? It dereferences Y and store whatever Y points to X. Both X and Y must be registers. Are we good so far? Okay. The other instruction that you also used in the previous lab was LDI. LDI looks kind of the same thing as LD, but it's different. Because instead of having Y as a register as the second operand, it has I as a placeholder. When you see I as a placeholder, it means it's immediate. Now, immediate is really just a fancy name of constant. Okay, what kind of constant are we talking about? You can give it a number. Okay, if 23 seems to be the right value, you can specify 23. On the other hand, you can also use a label. Okay, so in the previous lab assignment here, you saw how you can use a label in place of I, so that whatever the value of the label is now copied to the register X. Now remember, X is not a real register. It is just a placeholder to specify a register, one out of the 4 registers in the register bank. Okay, so we talked about that already. Do we have any questions about the LDI instruction? No questions? Okay, yes? All of these are placeholders. Yeah, so X, I, and Y are all placeholders. Okay, next one. What about the halt instruction? Does anyone have any questions about the halt instruction or what it does? There are 2 explanations. One is in column D, halt forever. What does that mean? Halt, stop, don't do anything. Do not proceed any further. Okay, and that's what the instruction does. Once you get to the halt instruction, it cannot move forward any further. You can keep clocking all day long, and it's not going to move forward. In the C explanation, which is kind of coincidental to column C, okay, it is just forever doing nothing. You cannot get out of this, okay? This is an infinite loop. It doesn't do a single thing other than consuming electricity and turning that into heat, okay? And that's what the halt instruction does. What about no op? Today you will use the no op instruction. What does it do? Absolutely nothing. Huh? Why is it useful? Well, it's not really useful. It's not so much that it is useful as it is a mandatory instruction. Look at the opcode. What is the opcode, the binary opcode of no op? 0, 0. Okay? Where do we get the fetch cycle? Yes?
Yeah, is it for delay?
Hmm?
Used for delay?
Used for delay? Well, you can use no op for delay, but it's really not a very good use. It's not a good way to delay something using just a no op or loop, busy loop to delay something. So no op is not really so much an instruction that then it is always there. Okay? Because when you execute the no op instruction, where do you think is the address of the slice in the ROM that corresponds to the no op instruction? 0, 0, 0, right? In hexadecimal, 0, 0, 0 in ROM corresponds to the slice that will perform the no op. That is basically what it is. Because all it does, okay, slice 0 of the entire ROM is doing what we call the fetch cycle. In other words, it uses the program counter to address RAM, and then it grabs whatever RAM has, put it into the instruction register, and then the next cycle, which is called the decode cycle, which is at location 001 in ROM, is going to do 2 things. It's going to decode, which means it copies the instruction. Okay, let me go back to the map here so we can see it. So the first one is called the fetch cycle. The fetch cycle is done by this particular bit pattern. And what it does is it establishes the pathway between the program counter to the address pin, and then it grabs whatever is presented on the data bus and put the content of that location, the address location, into the instruction register. That is called the fetch cycle. It is fetching an opcode from memory. Okay? All instructions start with a fetch cycle. The second cycle is called decode. Okay? So let's go ahead and do it. This is the decode cycle. How do I know? Because now we are addressing location 001 in ROM. So the decode cycle has two things to do. One is it is going to increment the program counter. The second one is it is going to copy the instruction register into the microcode pointer with one slight modification. What is the one modification? It's not just copying the instruction register to the microcode pointer. What else is it going to do? Shifting. It's going to shift it. So the instruction register will be copied over here, and it becomes 0, 0, 0 this time. Okay? Does that make sense? Now, how do we know that? How do we know that the microcode pointer is not just going to be incrementing, because it does have a mechanism to increment itself? Well, look at the selection of the multiplexer. The multiplexer says, what is this? Dark green is 0, which means it's choosing to connect input 0 to the output, right? Input 0 is coming from the instruction tunnel. The instruction tunnel connects to the output of the instruction register. So we know that the instruction register is supplying bit 4 to 11 of whatever is going to update the microcode pointer. Well, then what about the lowest 4 bits? They're all zeros. So this is why, when we update the microcode pointer, what is it going to be when we update it? If you just look at this picture. 0, 0, 0. Wait, didn't we just came from there? Didn't we just come from that part? So that's why the no instruction doesn't do a single thing, because look at two things. When I single clock again, look at the program counter, and also look at the microcode pointer. Okay, so I'm going to do Control T now. Okay, done. See how the program counter is now 0, 1? We advance to the next location to prepare to get the next opcode. If I do a Control T one more time, it will put the instruction code into the microcode pointer. So observe this part now. Control T, it goes back to 0, 0, 0. Did we do any computation? Nope. Did we move anything from RAM to one of the 4 registers in the register bank? Nope. That's why it's called no op, because it doesn't do a single thing. But it is not an intentional opcode. It is just that location 000 in ROM just turns out to be the fetch cycle followed by the decode cycle. So when you fetch and decode 000 itself, it goes back to, the next. It just goes to the next instruction without doing anything. Okay. So no op is not. It's basically just no operation. Yep.
So when the program hits halt, right?
Mm-hmm.
Halt command.
Mm-hmm.
Then it circles between those 000 and 001, right?
No. So when you get to the halt instruction, it does not cycle between 000 and 001. It is stuck at 010. The halt instruction is 01 in terms of opcode. So when you load it into the microcode pointer, it becomes 010. But when you look at the content of 010, they're all zeros. So the effect of that is we are not incrementing anything, and instead we are just, we keep updating the microcode pointer from the instruction register, which is 01 here, and we keep using that 01 to update the microcode pointer, which then becomes 010. So that's why it cannot go anywhere, because it keeps updating itself using the same value. Is that okay? But you can observe that, by running that experiment yourself as well. Okay. So do we have any questions about the no op instruction? Basically, it's not really an instruction. It is just that 000 corresponds to the fetch cycle, or how we start the execution of every single opcode. Okay. So we got that. Let's see. We have store, right? ST instruction. So what does the ST instruction do? The ST instruction is down here. So when you look at the English version of the explanation, it says store dereferenced. But when you look at the C code, that gives you more idea. So we get register X, and then we copy that to not Y register Y, but what register Y is pointing to, because we are dereferencing register Y in this case. That's why it's called store dereferenced. Are we good so far? Okay. So these are the instructions that we have kind of touched and used a little bit in the previous lab. So what we'll do today is to get to some of the other instructions. So we'll start with JMPI, which is here. So when we look at JMPI instruction, the English description is just jump with immediate destination, which means you tell me where you want me to go as a constant, so that every time you execute the JMPI instruction, a particular JMPI instruction, it always goes to a particular place. Is that okay? It does not depend on the register. Yes? Yes, 8-bit. So you can branch to any one of the 256 locations in RAM. Okay. But when you look at column C, it looks kind of weird, doesn't it? Okay. It says the program counter is whatever the program counter points to. What? Really? So what are we going to do? So let's say that you're trying to understand a particular instruction, and you really don't quite get what I'm saying here using the opcode table. What are you going to do? Squint harder. Frown. Pound on the computer. Shake it. Gently ask it. Google. Ask tech. Nah, that won't work, right? Tech will only tell you, figure it out yourself, right? So how do you figure it out yourself? Execute it. Exactly. So you write a small sample program using that instruction. And you formulate a hypothesis and go like, according to my understanding, this is what should happen. Okay? And then you single clock, Control T, Control T, Control T, Control T, and then you observe the control signal to all of those multiplexers, demultiplexers, enables of the register, select of RAM, and so on and so forth. And then you try to understand what is the processor actually doing clock by clock. Does that sound really tedious to you? Absolutely. But that is how you learn how the instructions execute. Now, once you have done this a few times, you'll kind of get used to it, okay? It doesn't get quite as daunting anymore, okay? But that is the best way to understand how an instruction works, okay? So what I'll do now is I'm pretending to be you and go like, well, I don't know how this works. So what I'll do is I'm going to go to my assembler, okay? And I'm going to write a very simple program using JMPI instruction, okay? So I go to the source here and go like, okay, I'm going to write some code here. I'll put a no op here, and then I use a JMPI to location 0. Okay? So what does line 1 do? Absolutely nothing except to move on to the next line, right? Okay, next line is JMPI 0. What does that do? Jump to location 0. So this becomes an infinite loop, right? Okay, so we want to know how it gets the job done. Okay, we have a theory that it is an infinite loop, It just alternates between line 1 and line 2, or these two instructions. But there's a second instruction. There's a second question. The second question is, how does the jump instruction get this done? Okay, what is the internal mechanism to get it done? Okay, so then we go to the RAM file, and we look at the program. Oh, that looks pretty simple, right? 0, 0, okay, as the first byte, which is the no op, and then 4, 0, which is the JMPI instruction, the opcode of JMPI, and then the second 0, 0 on row 3 corresponds to the address that we are branching to, which so happens to be 0, 0 as well. Okay, so now we switch back to the simulator, and then we enter this program. Okay, Control R to reset the entire TTP first, and then we enter the program. 0, 0 is already here. 0, 0 is already here. The only place I need to change is this place. Change it to 4, 0, and now I got the program. Okay, now for really simple programs, you can just do it this way. Just kind of hand copy the code. But if you have a longer program, obviously you want to download the RAM file and then right-click on the RAM and then load the image into the RAM. Okay, but for this program, it's simple enough. We know how to get this done. Okay, so the next thing we need to do is to say, well, do we know it is just alternating between the first and the second instruction? If you are not patient and you just want to confirm that this is an infinite loop, there's a quick way to do it. Observe the program counter. Okay, observe the program counter, and I will type Control K on the keyboard, which turns on the clocking. It's not single clocking; it's just keep clocking. And if you want it to be somewhat animated to the point where you can actually see what is going on, then you want to control the tick frequency so that it's not like 4.1 kilohertz. You can choose something like 16 hertz. It will still be able to see something on the screen changing. Okay, and now I'm doing Control K. Okay, so what I want you to do is to observe the program counter. It should alternate between 0, 0, which is the no op instruction, and 0, 1, which is the JMPI opcode, and 0, 2, which is the location that stores the address that I want to go to, and then back to 0, 0. Okay, so once again, if you observe this number here, it should be 0, 0, which is the address of the no op instruction. Then it moves on to 0, 1, which is the JMPI opcode. Then it moves on to 0, 2, which is the address of where I want to go to. It belongs to the JMPI instruction. That's the immediate part of the JMPI instruction. Then it goes back to 0, 0. Okay, so that's my theory, my hypothesis. Control K. Okay, well, looks like it's doing exactly that. Yep.
Why does it go back to 0, 0?
Because it uses the content at location 0, 2 in RAM and put it into the program counter itself. Okay? All right. So let's say that, okay, I'm convinced that this is an infinite loop doing absolutely nothing. Okay? So we do a Control K and go like, okay, we're going to stop here. So it is in the no op instruction, and I have no idea at which phase of the no op instruction. So it turns out to be at the very beginning of the no op instruction because we are at location 0, 0, 0 in the ROM. Okay? So now what do we do? Well, this time we are more careful. Okay? So we do a Control T this time, which is single clocking. Now we are decoding. Okay, we just fetch, we're decoding. And because the instruction or the opcode itself is 0, 0, so that means 0, 0 here is going to be padded with one extra 0, and and then microcode pointer will become 0, 0, 0 again. So you might think, oh, then we are stuck. Well, not quite, because the program counter is going to be incremented. How do I know the program counter is going to be incremented? Well, let's try to figure this out, okay? Because I'm assuming that you already know how to figure this out. Okay, so if you cannot figure this out, you have to let me know. So we look at the program counter, and the first question is it going to be updated? How do you know? Which pin of a register dictates whether the register is going to be changed or not? Enable, very good. So enable is this pin here. It has a light green line leading to it. What does that mean? It's a 1, right? So how do I know whether a 1 means enabled or whether 0 means enabled? Well, you can look up the reference. Okay, you can look up the library reference and understand what a 1 means to that pin. But I can tell you a 1 means it is enabled. Okay? When a register is enabled, it is waiting for a rising edge clock so that whatever is in the input becomes its current state. Is that okay? So now we just answered the first question. Yes, the program counter is going to be changed. It's going to be updated. So that should lead to an automatic second question. How is it going to be updated? Huh? Well, the clock is like a trigger. It is just saying that, yes, go ahead and update. But how is it getting updated? In other words, what is the new value? Who is specifying the new value to the program counter? Yes?
Well, the multiplexer sends in the address.
The multiplexer here, yes?
Yeah, sends the address
Is a 0, right? It's selecting 0, which means it's selecting input 0 to become the output, right?
Yeah.
So we track down input 0 now, right? We track down input 0, and where does it lead us to? The adder. Okay, this is an adder. How do we know it's an adder? You click on it, it will say that it is an adder here. Okay? This is an adder. Well, just because it's an adder doesn't automatically mean that it is adding, right? Because it depends on what you're presenting to the adder. Okay? Well, you look at this line here, it is green. So K0 or C in, carry in, is a 1. What about the other pin? This one comes through the program counter itself. So what we are now looking at is the program counter plus 1. It becomes the output. Okay? So if PC plus 1 is presented to the data pin of the program counter, and it is enabled, and we're going to have a rising edge clock, how do you think the program counter is going to be changed? It'll be increased by 1, okay? It's just PC gets PC plus 1, okay? So we control T, okay, which will give us the rising edge to actually update the program counter and see what happens to it. Ding. It becomes program counter plus 1. It increments, right? So this step, which is a part of the decode cycle, now the decode cycle has another thing to do, which happens at the falling edge, but we'll talk about that later. So as a part of the decode process, the program counter is incremented. Why? Because we are preparing to fetch the next opcode. Okay, this opcode is already fetched. It's already in the instruction register. I don't need the program counter to point to a place where it is already fetched. So the incrementing is to prepare the program counter to go to the next opcode. Okay? But there's one register in the entire processor that is sensitive to a falling edge. That is the microcode pointer. So the microcode pointer is negative edge or falling edge sensitive. So on the falling edge, what is the program microcode pointer going to do? Based on the control signals going into the microcode pointer, how do you think it's going to be changed? Well, let's figure it out. First thing, is it going to be updated, right? Bright green wire going to enable? Yep, it's going to be updated. Second question, what is its new value? Well, we track down the D pin. D pin comes from a multiplexer. The select of the multiplexer is a 0, which means we're connecting input 0 to the output of this multiplexer. Is that okay? What is feeding input 0 of this multiplexer? We know the least significant bits, 0 to 3, is just a constant 0. What about the more significant bits? Bit 4 to bit 11 comes from a tunnel called instruction. The tunnel called instruction is there. It's coming from the instruction register. The instruction register has 0, 0 because we just fetched that opcode from RAM. Okay? So on the falling edge, microcode pointer itself is going to go back to 0, 0, 0. Is that okay? Are we good so far? Okay. So I am actually assuming that you guys can perform this type of reasoning at this point because we understand how the individual components operate. Okay? If you are not really sure how the individual components operate, I have 2 steps for you to follow. The first step is try to use the help menu here, go to library reference, and click on the link to whatever you want to clarify. It's like, okay, I don't know how an adder works, okay? So you click on arithmetic, you go to the adder, and then you read the documentation of the adder and find out whether you understand what it means, okay? Now, if that works, good. If that does not work, then you let me know and I will try to explain that to you, okay? But this is what I'm assuming that you will be able to do, is to first find out how a component works. Okay. So Control T again, okay? It goes back to location 0 as expected. But this time, when we get back to location 0 in ROM, the program counter is not at location 0. The program counter is now 0, 1. And we are back to the fetch cycle, which means we can kind of expect the processor to go to location 0, 1, which is what the program counter is pointing to, get this thing into the instruction register. Is that okay? Well, is it going to do that? Well, how do we know that is going to happen? So once again, it has to do with the analysis of the components. First of all, are we going to change the instruction register? Yes, because enable is 1. Second question, what is the new value of the instruction register? How do we track that down? Look at what the D pin is connected to. So this D pin is actually easy to analyze because if you use the poke tool to poke on this D pin here, it goes all the way back to the D pin of RAM. So we know that we are connecting the D pin of RAM to the D pin of instruction register. Well, just because you're connected to RAM doesn't mean RAM is active or doing anything. So we look at all the control pins to the RAM. Well, RAM select is a 1, so RAM is definitely paying attention. 2, RAM load is also a 1, which means we are specifying a read operation so that the D pin of RAM is an output to the input of the D pin of the instruction register. Okay, so why is 40 highlighted in RAM? Who specified that address? Track it down. Okay, you track down the A pin. It goes to a multiplexer. This multiplexer has a select pin of 1 at this point, which means input 1 of this multiplexer is specifying the output. So we track down input 1. Input 1 connects to, not surprisingly, the program counter. So this is what I want you to do, is to track down how instructions execute by analyzing the components and also the tunnels of the processor. At first, it's going to be very time-consuming, it's going to be tedious, but once you get it done a few times, you'll get used to it. Yep? Right, until we get to the jump instruction. Yep. Okay, so we know that we are now going to get 40 from RAM and use that to update the instruction register. Okay, so we do a Control T, and not surprisingly, the instruction register is now a 40 because we have just fetched the opcode from RAM into the instruction register. Is that okay? After fetch, what is the next cycle? Decode. Okay, very good. So the decode cycle actually has 2 things to do. One is to increment the program counter. Okay, so the next rising edge is going to increment the program counter. Okay, this is the fetch cycle. So see how the program counter is now incremented to 0, 2. Okay, and then when we have the falling edge, then we will actually finish the decode. In other words, let's look at the microcode pointer and see how it's going to be updated. Are we going to update the microcode pointer? Yes. Okay, enable is on. Okay? What is the new value of the microcode pointer? It's specified by input 0 of the multiplexer. Input 0 of the multiplexer has all zeros for the least significant 4 bits. The most significant 8 bits come from the instruction tunnel, which comes from the instruction register, which is 40, right? So let me ask you then, knowing that the microcode pointer is sensitive to a falling edge, when I control T again, which means I clock it again, what is the new value of the microcode pointer? 400. Okay, very good. 400 in hexadecimal. And let's see. Yep, you're right. So this is the first slice of microcode corresponding to the JMPI instruction. So this is the big mystery, okay? Because the other stuff we have kind of explained already on Tuesday. But this is new, okay? How does the jump instruction know, or how does it get the job done to continue execution at a particular place? This will answer that question, okay? So when you want to look at one instruction and figure out how it gets the job done, you have to get the microcode pointer to point to the first byte or the first location corresponding to that particular code. So we are looking at the first microcode of the opcode. Is that sentence okay? Good? Okay. So we look at this, if you just keep staring at 1F80006, you're not going to get any answers, okay? So the way you analyze, the effect of this instruction is to look at the green lines, the light green lines, because that typically says what is active, what is going to be changed, and so on. So you scan the processor.
Is it active or high?
High. Active, high, they're typically the same thing. Yep, because in this particular processor, we use pretty much only active high signals. We don't use any active low signals. So we look for all the light green lines, but we really only pay attention to those that go into the enable, select, or something along that line. So when you look at the register bank, you go like, doesn't look like we're doing anything with the register bank, because none of the wire going into the register bank is light green, okay? They're all dark green. Everything is disabled. You look at the ALU, okay? The enable of the ALU is dark green. We are not using the ALU. You look at, let's pick out some other registers. Let's look at the flags register, okay? The flags register has also a dark green for its enable. We are not updating the flags register. We look at some other places, and let's see here. We look at RAM. Ooh, we're doing something with RAM for sure, because RAM select is a 1. So 1, yes, we know we are doing something with RAM, which automatically asks the second question. What are we doing with RAM? Are we reading or are we writing? Because those are the two operations. RAM load is also a 1. We are reading from RAM. Then you have two more questions to ask. Who dictates the location that we are reading from? And who is getting updated by the content of that location? So one question at a time. Who is driving the address bus? Track it down. You track down the address line, okay, which is this line here. It goes back to the multiplexer. The multiplexer has a select of 1, which means input 1 becomes the output. You track that down, and oh, guess what? The program counter is driving the address port of RAM. It's telling us which location we should be getting, okay? Next question. We know we are reading RAM, and the location is dictated by the program counter. Who is getting updated by the content at that location? That becomes the next question. So once again, we go to RAM, and we highlight the line or the wire connected to the D port, and then we ask which thing that it connects to is active. It goes to many places, right? It goes to the output of the register bank, but this is disabled. Okay, so that doesn't answer the question. We also know that the D port goes to the instruction register. but it's not getting updated because the instruction register has an enable of 0, so it's not getting updated. Okay, what else does it go? Well, let's track down. Okay, it also goes here. It goes into this particular multiplexer. So that particular multiplexer is switched by this pin here, okay? Now, you don't even have to figure out the math behind it. You just look at the bright green, and you say, oh, okay. So this multiplexer is selecting input 1. This is input 0. This is input 1. So this input becomes now the output of that multiplexer, okay? You track it down a little bit further, this wire. So this wire in return goes to another multiplexer, okay, as an input. This multiplexer has a select of 1, which means it is selecting input 1, which is the one we are highlighting, to become its output. Okay, let's follow that. So now we update, we follow this, and guess what? It goes into the program counter. Okay, well, just because it goes into the program counter doesn't mean that it's going to do anything. But wait, we are doing something with the program counter, aren't we? Because the enable of the program counter is a 1. So the program counter is already enabled for an update. It's really just waiting for a rising edge at the clock to perform the actual update. So when we type Control-T on the keyboard, what do you think is going to be the new content of the program counter? 0, 0. Because location 02 in RAM has the content of 0, 0. That content, through the multiplexers, goes back to the input of the program counter. This is why the documentation says PC equals star PC. Because we are using the program counter to specify which RAM location to read from, and then we grab the content to update the program counter itself. Okay, let me switch back to the opcode table and show you what I meant by that. So we go back to here. See how this, how I document the jump I instruction? It's PC equals to star PC. And that is exactly why I wrote it that way. So are we good so far with the unconditional branch instruction? Okay. So we'll go ahead and just confirm that by clicking it a few more times. So when I click Control-T again, the program counter will be back to 0, like that, okay? And then when I click it one more time, now remember the microcode pointer is falling edge sensitive, so that means it is about to be updated. So this is the mysterious part, okay? So when we update the microcode pointer, where is it going to go? Let's try to figure it out, right? The input of the microcode pointer, or the D port, connects to the multiplexer. The multiplexer is selecting input 1 to go to the output. Input 1 is coming from the adder, so we are really just incrementing the microcode pointer. Is that okay? So when I Control-T, what do you think is going to be the new value of microcode pointer? It's a semi-tricky question. We are incrementing the microcode pointer. 401. Okay, very good. So we'll go ahead and do it. And you were right. You were actually right that it was 401, but it only stayed in 401 for a tiny fraction of a second. We couldn't see it. And you go like, what is at location 401 that it was just going to go there for a very brief amount of time and so fast that we couldn't see it, so that we almost just think that it went from 400 all the way back to 000. What is going on here? So now what we want to do is to look at that location 401 and find out exactly what is there, okay? So here's 400, this is 401. Doesn't look too complicated. It's 2 followed by a bunch of zeros, right? In other words, only one of the 26 bits is a 1. The rest are all zeros, okay? But we want to know which bit is that 1, okay? Each hexadecimal digit is 4 bits, okay? So we got 1, 2, 3, 4, 5, 6 zeros. So that accounts for 24 zeros. 2 itself is 1 0, so we got 1 extra 0, so we got 25 zeros, right? So we have 1 followed by 25 zeros. In other words, bit 25 is the one that is on. All the other bits are off. So now you go back to the design, you go back to the processor, and ask, what is so special about bit 25 coming out of the ROM? This is bit 25. Where does it go? It goes to the OR gate, okay. Wait, if it goes to the OR gate, that means if it is a 1, then the output of the OR gate is also going to be a 1, right? Okay, so we need to track down where the OR gate is going. The OR gate goes to the reset of the microcode pointer register. So what happens when the reset pin of a register is a 1? It resets the register back to 0. Okay, and it happens instantaneously. It doesn't wait for the clock to have an edge. Okay, whenever the reset pin of a register is a 1, it just zeroes out the content of the register. It does not wait for a clock edge. That is why when we incremented from 400 to 401, you are absolutely correct that it actually went to location 401. But as soon as it went to location 401, the output of the ROM is going to make this Y a 1, which in return makes this Y a 1, which in return resets the register, and it went back to 0 in a tiny fraction of a second. So from our perception, we just go like, it went from 400 to 000. No, in reality, it went from 400 to 401 for a very short amount of time, then it went back to 000. Is that okay? So that sequence of bits is very important to basically terminate the last microcode corresponding to an opcode so that we go back to the fetch cycle. So we are now ready to get the next opcode. Are we doing okay so far? Yep. Oh.
I wasn't sure if I was the one you were pointing at or not.
Oh.
I had just a quick point of clarification. Can you explain what would be the purpose of incrementing the microcode pointer?
So we can go to the next microcode, the next microcode, the next microcode.
But don't you choose which microcode to point at based on the instructions that you receive from them?
Okay, so the original intent of this architecture is I might want to implement some complicated stuff, okay, where one single microcode is not enough to finish the operation. So I want to have the flexibility of saying, oh, I will need 5 microcode to complete what this opcode needs to do. So I have that provision. It just turns out that, because I am using the RISC design philosophy, so that means, all the instructions are very simple, and it turns out they only need one single microcode.
So that goes back to why you have all those extra zeros.
Exactly.
Okay.
Yep. So when you look at the content of the ROM, we see all these extra zeros. Okay. What's going on here? How come these are all zeros? Because I overestimated how much I would need to implement the instructions by a whole lot. And that's why. Yep.
For the instruction register, what it means 40?
40.
Yeah, 40.
Uh-huh.
How did you know the Ucode pointer would be 400?
Because the instruction tunnel goes here. It combines with that extra constant 0 here, and that in return through the multiplexer is going to update the register. but it depends on the switch, right? It depends on this select line. So sometimes I just want to increment, and but in the event that I want to decode, then it will select input 0 in order to take this and that into here. So are we doing okay so far? Doing okay? Yep.
Does that mean every single subsequent microcode has that reset?
Yep. Exactly. So that's good observation or good hypothesis. So you can actually see how every single useful opcode ends with that sequence. Yep. Good observation. Okay, any other questions before we move on to conditional branches? The good stuff. Or the increment instruction. Well, pick one. Which one do you want me to talk about first? How about we talk about compare first? Okay? So let's go ahead and write a program to do some comparison. Okay? Simple stuff. So we go back to the assembler, go back to the source tab, and then we'll go ahead and write a compare instruction. Okay? Without any conditional branch. So, okay? So LDI A with 2, LDI B with, I don't know. Do you guys want it to be tricky? Yeah, let's make it tricky. 255. And then we do a compare AB. Okay? So compare AB, okay, so do we have any questions about the first two lines, what they do? Hopefully not. Okay? So A gets the value of 2, and then B gets the value of 255. Now remember, 2 is always 2, signed or unsigned, but 255 is really just specifying 1111, 1111. What does it represent? I don't know, right? Because it depends. If it is unsigned, it is 255. If it is signed, it is -1. Okay? So remember what I said when we talked about binary comparison? We don't ask that question. Okay? What is 1111, 1111? What is it representing? Don't ask me that question until that bit pattern is actually used. Yep?
But doesn't it do like a NAND comparison, bit by bit?
It would do a subtraction. It will do a subtraction. So I'm just going to halt the instruction here. Okay, so I'm going to, oops. Lowercase, uppercase is fine. It actually does, it changes everything to lowercase before doing symbolic processing. So we'll put a halt instruction here. The question is, by the time we get to the halt instruction, which flag is going to be a 0, which flag is going to be a 1? Well, we won't know until we know, how the compare instruction works, right? What it does. So to understand that, we go to the opcode table. We look up the CMP mnemonic, and it's right here. This is the CMP instruction. The English version of the explanation is just compare, okay? The C explanation is even worse. It says x minus y. But what are we doing with x minus y? Nothing. Then why are we doing it? To set the flags. Okay? So we are, in fact, carrying out a subtraction. We are taking the register that is represented by x, and then we are subtracting the register represented by y from x. Okay? We are actually performing the subtraction, just like the logic in the binary subtraction module talks about. Okay? So we carry out that subtraction. We are not doing a single thing about the difference. We are not storing the difference at all. Okay? But it still changes all the flags. So now you have to remember, oh, we got 5 flags, right? The carry flag, which is also known as the borrow flag, the overflow flag, the 0 flag, the sign flag, and also the L flag. Okay? So you have to now think about all of those flags and go like, What is it going to do? What is the program going to do to the flags this time? Okay, so we can comment. Okay, you can actually write comments in this program. So we'll take a look. Do you think the carry flag is going to be cleared or set? Remember, the carry flag is only useful when you look at things from the unsigned perspective. Is 2 less than 255? Come on, yes. Okay, the 0 flag is the result of the subtraction 0. Not 0, okay. ZZ sign, okay. From the signed perspective, from the signed perspective, now you have to be really, really careful. Because are we talking about 2 minus 255? Or are we talking about 2 minus negative 1? If it is the signed perspective, the bit pattern of 1111, 1111 is representing which value? Negative 1. 2 minus negative 1 has a sign of 0, because 2 minus negative 1 is 3, right? What about the overflow flag? Can 3 be represented using 8 bits? Yes, and therefore the overflow flag is 0. Very good. And what about the L flag? The L flag is the exclusive OR between the sign and the overflow flag. Looks like it should be a 0, right? Does that make sense? Because the L flag is saying 2 is not less than negative 1. Is that true? 2 is not less than negative 1. That's why the L flag is cleared, because the L flag is a 1 if and only if x is less than y in a compare using the signed perspective. Okay? So I'm writing this out so that we can later on compare what is in the flags register to what we see here. So are we good so far? Okay? Let's go ahead and run the program. So to run the program, you go to the RAM file tab. And this one is kind of long. I don't feel like typing it. So we just download it as a CSV or TSV. Okay, you can pick either one. And we'll just call that CMP. Switch to the simulator. Control R to reset the whole thing because I can actually clear the RAM. This is a new program. Right click, load image, and it's called cmp.csv. We got the program in. Now, if you want to single clock it, that's okay. That's perfectly fine. In fact, I highly encourage that you guys single clock it, especially for the compare instruction itself, just to see how it works. Okay, how does it send register A to input 1 of the ALU? How does it send register B to input 2 of the ALU? How does it update the flags register? Blah blah blah. Okay, but you need to spend the time to do that. Okay, because otherwise it's not gonna but it's straightforward enough that you can actually do that. Okay, so that's kind of something that you have to do. So what I'll do is I'm just going to do a Control K to run all the way to the end of the program. Now we are stuck. Now, how do we know we are stuck? How do we know we are now at the halt instruction? There are several ways to tell you. Okay, you can choose whatever works best for you. Well, okay, so you can see the program counter is not changing at all. You can also see the microcode pointer is not moving at all. But best of all, you can see that the halt pin is a 1. Now, if you say, Tech, that's really tricky. You make this halt pin kind of small at a really, really off place. Well, you can change your version of the processor, okay? If this is too non-obvious to you, then you go to, let's see here, I guess it's input-output. Get yourself a bunch of these things. Wire them up together. Okay, here we go. and hook them all up to this pin. Just keep doing this. Uh-oh, I clicked something. But you get the idea, right? You can make it very obvious in your version of the processor, okay? What I did was I clicked, now it's moving forward because I accidentally touched one of these things. I cannot, Control R, maybe I click Control R. I bet you that's what I did. Okay, let's do Control K, stop the whole thing, go back to the content. Nope, the program is still here. I did something to make it go, move forward again. I have to be clicking something. I know what I clicked. No, it cannot be that one. Well, it's all getting recorded. I can go back in time and watch it. Yep. Well, that reminds me of one thing. When you are writing programs, you can actually use OBS to record your whole session of writing a program. So that, let's say you did something and then the program doesn't work anymore and you cannot remember what you did, okay? Which variable did I change? Did I change this comparison? Did I move this loop out of this here and whatnot? If you cannot remember, now the best way to do it is to use GitHub or some other revision control software. But since you can do screen recording, just screen record your entire programming session, okay? So this way, if you cannot remember what you did to break the program, play back that recording so that you can actually see what you did to break your program. Now, in the good old days, it would not have been a practical solution because my entire hard drive only has 20 megabytes. How much hard drive space do you have on your laptop? Let's say you only get 1 terabyte and go like, I don't want to waste my space. I got all the movies saved up here. But go to Costco, buy yourself a 3 terabyte external hard drive and record all your programming sessions, okay? So that you can, if you make a mistake, you can play back and the whole thing and go like, oh, so that's what I did. Tools that I never had, you guys have now. Okay. So, are we good so far? Okay, so we need to reset the whole program because I need to get to the flags register, right? So we have to go back here and reload that image, okay? And then type Control K again and make sure it gets stuck. Okay, now it's stuck. So we have to look at the flags register now, okay? So when we look at the flags register, the value of a register is always on its face. So the flags register has 0, 1 on its face. So now the question is, so that tells us that the flags register is 00000001. But which bit is which flag? That becomes the next question. The flags register cannot tell you that, but the ALU can. So when you go to the ALU, you go all the way to the bottom of the whole thing. This is the flags out. But when you look at this particular splitter, that tells you which bit is corresponding to which flag. Bit 0 is carry. Bit 1 is 0. Bit 2 is sign. Bit 3 is overflow. And then bit 4 is the L flag. Okay? Well, that just kind of corresponds to the way I type the program. So when you go back and read my comment, when I type in the source code, that's exactly in that order. The carry flag is bit 0, and that's the only one that is a 1. So this kind of verifies that, oh yeah, we got it. Okay, we understand how the flags register work, especially in the case of a compare instruction. So are we good so far? Yes? Yep.
If we change the compare AB to compare BA,
Uh-huh.
would they change?
Absolutely. So I can give you an idea of what it is going to do, okay? So this is now becoming B minus A, okay? So let's work this out. So the question is, does 255 minus 2 require a carry? No, we don't need a carry, okay? So the carry flag is going to be 0. Is the result 0? No. CZS, okay? Is the result signed? Is the result negative when we look at it as a negative number? The answer is, so now you have to be careful because we are not thinking about 255 minus 2 because the bit pattern that represents 255 unsigned is representing what value signed? Negative 1. Okay, so you have to think about negative 1 minus 2. Is negative 1 minus 2 negative? Yes, okay, because it's negative 3. Can negative 3 be represented using A bits? Yeah, sure. So there's no overflow. What about the L flag? What is the exclusive OR between the sign and the overflow flag? It's a, no, it's a 1 because they're different, okay? So this is the projected output of the flags register. It is 1, it's 0. So we have to read it backwards, remember, because the L flag is actually the most significant bit in the flags register. So it's actually 1, 0, 1, 0, 0. Or when you look at the register on the face, it becomes 1, 4 because those are in hexadecimal. Okay, so we're expecting 1, 4. Okay, do you guys want to kind of double check on this one? Sure, okay. So if I'm really lazy and I go like, I don't want to change the program, how am I going to modify the bytes so that it is doing this? In other words, all I'm doing is to reverse the comparison. Instead of A minus B, is now B minus A. I only need to change 1 byte, right? Only 1 opcode is responsible for that compare instruction. The rest of the program stays the same. So now the question is, which byte am I going to modify, and how am I going to modify that byte? Okay. Well, the LDI instructions takes 2 bytes each. Okay. So that means byte 0 and byte 1 corresponds to LDI A2. Byte 2 and 3 corresponds to LDI B255. So CMP BA is going to be byte 4, byte 4, okay? So byte 4 is the CMP BA instruction. That particular byte has 2 bits to specify the first register, which I swap from A to B, and then it has 2 bits to specify the other register, which I swap from B to A, okay? So I have to exchange only those 2 bits, and they are the least significant bits, okay? So without looking at the assembled output, I just kind of go back to my Logisim here, and then we go to the RAM component. It is byte 4, which is this E1, okay? And I can't change it. Okay, maybe I need to use the poke tool. Okay, there we go. So E1 needs to be changed. Now, the E part I don't want to change because that's the part that is always going to be there for all compare instruction. 0001 is specifying register A and register B respectively. I need to change that to 0100. But 0100 binary is 4 in hexadecimal. So now we have E4 instead. Okay? So let's go ahead and check this out. Okay? I need to reset the processor without resetting the RAM. So if you want to do that sort of a trick, the first thing you need to make sure is clock is low. So clock is low now, which is good. Then you hit the reset button. The reset button resets everything except RAM. RAM has its own reset button, so I'm not resetting RAM at all. So now I can actually run the program again. Control K, it keeps going, it stops, and then we look into the flags register, 14, which was what I said. Okay, so we got about 5 minutes. We'll have to finish this discussion so that you can get started with your assignment. So we're going to have to stay here a little bit. It has to do with the conditional branch instruction. So the conditional branch instruction is usually happening after a CMP instruction. So in this case, because we know that L flag is going to be a 1, we're going to say JLI, okay, jump if and only if the L flag is a 1 to a particular label, say L2, okay? And then over here we have a halt instruction. And then at the label L2, we're going to say halt again. So the question is, which halt is it going to go to? Okay, where are we stopping this entire program? That's the question. What do you think? The one on row 7. That is correct. Because JLI says jump if and only if the L flag is set. Well, in this case, the L flag is in fact going to be set. So it will basically, this becomes a conditional branch, and it goes to label L2. It does not go to row 5 at all. Okay? On the other hand, if I change this instruction to JZI, okay, JZI L2, then it will stop on row 5, because the Z flag is a 0 after the comparison. And this is now saying jump if and only if the 0 flag is a 1. Well, the 0 flag is not a 1, so don't jump. What do I do if I don't jump? Well, just go to the next instruction. Okay? I don't have enough time to explain how it works. Okay? So, you guys, should spend some time to figure out, how the conditional branch instruction works. So, but I do need to explain one more thing before you go to the lab. It has to do with the instruction of the lab, the last step of the lab instruction. So let me go back to the lab instruction here. The last one. So the last one involves having to log stuff using Logisim. So you just copy and paste that code, put in your student ID. And then what you need to do is to count the number of times a particular instruction executes. And the part that you have to be careful about is the logging part. So let me switch back to Logisim. So the logging part has to do with this part here. Okay, so you go to logging down here, and then you can specify what you want to log. The instruction of the lab actually tells you what you need to log, okay? So typically what you need to log in most cases would be the program counter, okay? So you go to the program counter, you say, okay, I want to log the program counter, and by default it is logging in binary, which is really kind of hideous. So you want to change the radix to 16, change it to base 16, which is hexadecimal. You probably want to log some of the other stuff. This is not register A, by the way. This is the address port A. This is the data port D. So if you want to get to the registers, or you can also log the flags. Okay, you can log the flags register and change the radix to base 16 and so on. Okay, so the one thing that you have to be careful about is when you specify a file. Okay, you'll specify a file here. So we'll say test.tsv. Okay, and we say enable. The problem is it will keep appending to this file, and you would not be able to tell that it is just a continuation. So when you count how many times you have been to a particular location, you'll be recounting steps from previous experiments. Okay, so you have to be extra careful about that part. And when we go to I think it's the user's guide, and we go to logging, it actually tells us how to reset the file. So when you go to the File tab, let's see here. Okay, this button allows you to pause and restart file entry. So the button that they're referring to here is an indicator whether the file logging is in progress, and a button for enable and disabling it. So they're referring to this button here. So between experiments, you have to disable and then re-enable it, so that it doesn't keep logging to the same file. Okay. Okay. So let's run through this once, so that I can actually show you what I mean by that. Okay. So we go back to simulate. We go to logging. and it is now enabled. Oh, now it's disabled, and I click it, now it is enabled. So you read the text here to see the current state of what you have specified. And the log file, you cannot probably see it, it's test.tsv. So we close the window, okay? We reset the main processor without resetting RAM. So RAM is still intact, and then we just do a Control K, so it automatically is run all the way to the end. Now this, at the end, we type Control K again, and then we go to that location, which is in the temp folder. It's called test.tsv, and this is the log. So this tells us that the program counter, has the values, 6, 6, 0, 1, 2, 3, 4, 5, 5, 5. And then the last 6, has to do with the auto increment because of the decode cycle, okay? Now, let's go back to the simulator, and let's just say that, okay, I need to run the experiment again, okay? Without doing a single thing, okay? So I go to here, I make sure the clock is low, hit the reset button of the main processor, so the RAM is now, is still intact, and run it again, okay? It will continue to log. Control K, it logs again. We go back to the file and update the file. Oh, it's just appending it, okay? So I want it to reset, right? So how do you reset it? You go back to the simulator, okay? We repeat the same experiment again. And this time, make sure the clock is low before you reset. And then we try to run again. But don't run it yet. Go back to simulate. Go to logging. Disable first. Then re-enable, okay? And then click this window. Close that window. Control K. Control K again to stop the simulator. And when I update, it did not actually reset the file. You can always create a new file or delete the file that you already have. So if you delete the file that you have already created, that will work too. So if I go back to here and, okay, so the instruction was actually incorrect. It does not actually reset it. Okay. Control K, start the whole thing, stop, go back and look at the file again. So this time it did reset it. So just be very careful about that last step of the lab, because if you don't delete the file, it will keep appending to the same file. Now you can also just choose to use different files, one file for each conditional branch instruction. That works too. All right, so I'm going to go to the lab, after I shut down everything here. Hold on a second. I think, okay, there you go. JXI, lowercase,